This is the main question. Phi is not considered to be smooth. And for non-smooth object, there is a recent field called C0 symplectic geometry, which studies homeomorphisms, symplectic analogs, continuous symplectic analogs of notions from symplectic geometry, such that symplectic homeomorphism or Hamiltonian homeomorphisms. And for this talk, it will be important the following notion, which is notion of a Hamiltonian homeomorphism of M, and the set of Hamiltonian homeomorphisms are just closure of the group of homeomorphisms, the group of Hamiltonian diffeomorphisms in the larger set of homeomorphisms of M. So we say that this consists of all homeomorphisms phi of M such that phi is a uniform limit of a sequence of symplectic Hamiltonian diffeomorphism. And in general, fixed points of homeomorphisms were extensively studied in dimension 2, and it started probably with work of Brouwer, and there is Poincaré-Birkhoff theorem. And in fact, it was shown by Matsumoto that this conjecture is true for homeomorphisms. The Arnold, this is his theorem. The Arnold conjecture holds for Hamiltonian homeomorphisms in dimension 2, which means that if we have Hamiltonian homeomorphisms of the sphere, Hamiltonian homeomorphism of the sphere, then it must have at least 2 fixed points, and if we have Hamiltonian homeomorphism of surface of genus 1 and higher, it must have at least 3 different fixed points. And in this case, in case of dimension 2, Hamiltonian homeomorphisms of a surface are precisely those which are area and orientation preserving, isotopic to identity, homotopic to identity, and having zero mean rotation vector. So these are exactly those which were studied by topological dynamists before. And it's natural to ask if one can show the C0 Arnold conjecture also in high-dimensional case, but it turns out that in dimension 4 and higher, this statement is fails completely. So the theorem joined with Vincent Humilier and Sobhan Seyfeddini states that if we have any closed symplectic manifold of dimension at least 4, then one can construct a Hamiltonian homeomorphism such that phi has exactly one fixed point. So one fixed point, you cannot find Hamiltonian homeomorphism without fixed points because each such phi is a uniform limit of phi k, and by Floer theory, phi k has one fixed point at least. So phi must have at least one fixed point, but there are examples where it's exactly one. So this might seem that this completely destroys C0 Arnold conjecture, but actually in the rest of the talk I would like to explain that how to rescue C0 Arnold conjecture. So and in fact one can do it by giving a slightly stronger formulation in terms of action spectrum and fixed points. And the origins of this formulation goes back to Lusternik-Schnirelmann theory. So let me recall some basic notions and state corresponding result for the case of smooth functions on closed manifolds from Lusternik-Schnirelmann theory. So so here we consider M to be a closed manifold and F any smooth function. We study F by looking at sublevel sets. So we consider the following subset of M, MT. These are all points where F is less than T. And we look how the homology of MT changes when we increase T. So when T is very large, then MT is just M. So the homology of MT is homology of M. And when T is very small, then homology is 0. And for if S less than T, then MS embeds into MT. So we have corresponding map from homology of MS to homology of MT. And we can consider, we can study how homology changes. When T increases, some classes might appear, then some might disappear. And in the limit at infinity, some classes remains, which are exactly homology classes of M. And we can define the notion of spectral invariants corresponding to this function F. For any, if we have a homology class alpha, then we define the corresponding spectral invariant to be infimum of the level from which this homology class appears in the homology of our MS. So this is infimum of S such that alpha lies in the image of homology MS in homology of M. And once it appears, it stays forever. So, for example, just to illustrate, we can look at the torus as drawn in the picture and the height function. Then we have here 4 critical levels. And for example, in first homology, one generator is this cycle, and it appears exactly at this level, the second level, and another is cycle with goes around the hole, and it appears in the third level. So before we reach the second level, the sublevel set is just a disk, but after we pass this level, it closes here and the cycle appears. And the following statement was proved by Bursztyn and Schnirelmann. I will state it as lemma that suppose we have 2 homology classes in M. Degree of one of them is less than the dimension, and their intersection is non-zero. Then, and now assume that we are given a smooth function f such that the 2 spectral invariants coincide for alpha intersection beta and alpha. Then statement is that it's a kind of degenerate situation, and in this case, if we consider the set of critical points of F line on this level set, then it's homologically non-trivial. So the set crit F intersection with F equal to this number is homologically non-trivial, and hence the set is infinite in particular. So here I use this terminology of homologically non-trivial. It means that the set contains non-trivial homology class of M. So we say that A is homologically non-trivial in M if for some positive J, the image of homology of A inside homology of M is non-zero. And corollary of this lemma is the Bursztyn-Schnirelmann theorem that exactly analog of the Arnold conjecture. So corollary yes. So I look at all the points in M where F is equal to this. Yeah, it's a level set. Yeah. So, so the corollary that if F is smooth, then either the number of spectral invariants of different spectral invariants is at least cup length of m plus 1, or the set of critical points of F is homologically non-trivial, and in particular infinite. Of course, in this case, this condition guarantees that there are at least, in the first case, there are at least this number of critical points if we have this number at least of critical values. So this actually means that there are at least cup length of m plus 1 critical points always, but I still want to consider exactly this formulation. So now let's pass to the symplectic setting. So all this, so these notions can also be defined in the case when we have a closed symplectic manifold, and I will assume almost always that it's symplectically aspherical. And the Floer homology is homology of action functional on the space of contractible smooth loops or in M. So one can try to mimic what we have done until now. So I will use the following notation. If H is a time-dependent Hamiltonian function, then we get a flow which I denote by phi ht. And we have the action functional on the space of loops with in M which are contractible. So so U is a filling disk of the loop. And critical points of this action functional are exactly one periodic orbits of the flow. And we can try to do the same as we did in the Sтерnik-Schneermann theory. So we consider the Floer complex of our function h, and we have Floer differential, and we get Floer homology of h, which is isomorphic to just homology of M by PSS isomorphism. And but the Floer differential respects the natural filtration by the action functional. So we can look at, for any t, we can look at subcomplex of those periodic orbits with action less than t, and this gives us the Floer homology group for any t. And as before, it is 0 for t very small, and it is equal to the Floer homology, the full Floer homology if t is very large. And as before, we define if alpha is homology class of M, then the spectral invariant is infimum of all t, such that the corresponding PSS of alpha lies in the image of this map. So we have a map from our homology HF less than t to HF. So in this case, we also have the notion of spectral invariants, and it is important to remark that in the symplectic spherical case, they are almost dependent only on time one map. So this was shown by Schwarz and Seidel. If we, and this holds only in the symplectic spherical case, if we have two Hamiltonian functions with the same time one map, then all spectral invariants, the spectral invariants of one Hamiltonian are just shifted spectral invariants of another Hamiltonian. So this means there exists some constant such that we have C alpha h is C alpha k plus this constant for any alpha in HM. So the spectral invariants of just of Hamiltonian diffeomorphisms are well defined up to shift. And in particular, one can speak about the number of spectral invariants of given phi. In fact, this lemma from Lusternik-Schnirelmann theory and its corollary, they do hold also in this symplectic setting, and it was shown by Howard. So I will just formulate the corollary as a theorem that so let's M omega be symplectically spherical. And let phi be in Ham M omega. Then either the number of spectral invariants of phi is at least cup length of m plus 1, or the fixed point set of phi, the set of the fixed points of phi is homologically non-trivial. And in particular, infinite set. So, and the one of the result that I want to explain is that, in fact, it was observed by Vincent Humilier, Sobhan Seyfadini, and myself, that this statement is also true for Hamiltonian homeomorphisms. So Howard's theorem also holds for phi inside Ham bar. And actually the proof goes in a similar way. But in order to, and also later, this the same thing was shown also by Kawamoto for CPN and negative monotone case. But okay, one can need to be more precise here since it's not symplectically a spherical case. But anyway, in order to state that it's true for Hamiltonian homeomorphism, one needs to make sense of, to explain what are spectral invariants of Hamiltonian homeomorphisms, because Hamiltonian homeomorphism is just a homeomorphism. One cannot do Floer theory with it in a direct way, and it's not a time-one map of any flow a priori, and everything is continuous. But in fact, what turns out that there exists certain C0 continuity of spectral invariants, and which I want to explain, and the better way to do it is by using the notion of gamma distance, gamma norm. So this is a notion which was first introduced by Viterbo in case of R2n or cotangent bundle using generating functions, then extended by Schwarz to symplectically aspherical manifolds, and also by O to general case. And if we have a Hamiltonian diffeomorphism, then we define gamma of phi to be the difference between the largest and smallest spectral invariant the one corresponding to the fundamental class minus the one corresponding to class of the point. And this notion, it turns out that gamma is in fact a norm on group of Hamiltonian diffeomorphisms. So this, so each one of these is not so well defined. It's up to shift, but the difference is well defined, and gamma is in fact a norm on Ham, and the result that I want to state is the result states that the C0 continuity of gamma. So This is a theorem again joined with Humilier and Seyfadini, that if M omega is symplectically aspherical, then gamma is C0 continuous. So it means that if we have a sequence of Hamiltonian diffeomorphism which converge to the identity in the uniform way, that then gamma of phi k converge to 0. And this is a basic fact which again, this result was also so before we did this for closed symplectically aspherical case, Viterbo have shown this in the case of R to N, then Seyfadini in 2012 showed that it's true in dimension 2. And after it appeared, Sheluchin have shown it for CPN, and later Kawamoto found a different proof for CPN and showed also this for negatively monotone closed symplectic manifold. And but let's come back to the symplectically aspherical case. So by properties of spectral invariants, which I did not state, but in fact the C0 continuity of gamma implies that C0 continuity of all spectral invariants up to shift, and that one can, yes. I'm sorry. Yes, I wanted to speak about it later a bit, but if you're talking about Hamiltonian homeomorphisms. Yeah, in the smooth case it cannot happen, but in the case of in the continuous case, you might think there is some contradiction, because we get that there are many spectral invariants. There are many spectral invariants, but only one fixed point. But this is not a contradiction. It's how life is. But it turns out that in high dimensions, fixed points are not very good notion. They can collapse to one point, and this point is fixed point with, you can say, with high multiplicity, but it's also a bit strange that it contains in itself, in some sense, many fixed points with different actions. So I will come back to this again and speak again also about two-dimensional case. But let me just say that C0 continuity of gamma implies that C0 continuity of spectral invariants up to shift, and also that we can define spectral invariants for Hamiltonian homeomorphisms. So this is corollary that can define spectral invariants up to shift for phi inside the closure of Ham. This means that if phi is in closure of Ham, then we know that there exists a sequence of Hamiltonian diffeomorphism which converge C0 to phi, and phi k is in Ham. And then one can express C0 continuity of spectral invariants up to shift by saying that for any two homology classes, alpha and beta, there exists a limit of difference between spectral invariants for alpha and spectral invariants for beta, which one can denote it as, for example, gamma, alpha, beta, phi. And existence of such limit for any alpha and beta mean that one can just define this collection of spectral invariants well defined up to shift. But actually, I would like to remark that the spectral invariants, they detect only part of filtered complex, the homology of filtered complex, and in fact, more precise notion is a notion of barcode. So this is can be drawn as a collection of half-infinite intervals and also finite intervals. So the half-infinite intervals correspond to spectral invariants. Once once the homology class appears, it stays forever, and the bars correspond to appearing and vanishing elements of filtered homology. So, so in fact, this is a more precise notion, and C0 continuity of gamma, if we have C0 continuity of gamma, for example, in symplectically spherical case, and we have continuity of barcode with respect to gamma. And this result was proved by Kislev and Shilukhin. That in fact barcode of phi depends continuously on phi when we consider gamma distance, the topology given by gamma distance, and there exists certain distance on the space of barcodes called bottleneck distance, and Kislev and Shilukhin proved inequality between bottleneck distance and gamma. But if we have these two together, this implies that we can define a barcode which encodes all the filtered floor homology for any phi inside Ham bar, for any Hamiltonian homeomorphism. And this was previously, so this is an observation of Shilukhin, and it was previously proved by Leroux in a direct way the last statement by Leroussi, Fadini, and Viterbo in dimension 2. Okay, so let's come back to the Arnold conjecture, and as we saw, so if we speak about Hamiltonian homeomorphisms, then Hamiltonian homeomorphism can have only one fixed point and many spectral invariants. And so this high dimensions allows to collapse the fixed points to 1. And the fact that there are many spectral invariants does not mean that we have many fixed points. But our hope with Vinson and Sobhan that in dimension 2, this fact of having many spectral invariants will give us, in fact, many fixed points. That 2 dimension does not allow to collapse the fixed points to 1. And the obstacle, one of the obstacles is the existence of many spectral invariants. And another is lower dimension, then this hopefully will lead to many fixed points and give another approach to theorem of Matsumoto. And so the main lemma here, which I think we have proved, so this is work in progress, and I will not state it as a proved result, but is the following, that let's assume that we have a closed 2-dimensional surface with area form, and I assume that genus at least 1. It's not, genus 0 can be also formulated in a similar way. Then assume that that we have some phi in which is a Hamiltonian homeomorphism of M, and assume that it has a finite number of fixed points. Now we know that phi is a limit, C0 limit of a sequence of Hamiltonian diffeomorphism. One can approximate it up to any epsilon in C0 distance by Hamiltonian diffeomorphism. And if this Hamiltonian diffeomorphism is very close to phi, then if we look at fixed points of psi, then they lie in neighborhoods of these fixed points. And the statement is that one can find there exists a perturbation psi such that near each fixed points of phi, all fixed points of psi have almost the same action. So this is true in case of, in the smooth case, if we have a Hamiltonian diffeomorphism with degenerate fixed points and we perturb a little bit, then all the actions of fixed points appearing near one fixed points are almost the same. But in the continuous case, it's completely not clear. So this is the main lemma, and if it's true, then the theorem of Matsumoto, at least in case genus at least 1, will follow. So if we assume that, for example, we have on the torus not 3 but only 2 fixed points, then by perturbation we get our psi with collection of fixed points near each one of these two. And all the actions here are close to each other, and all actions here are close to each other, which will imply eventually that phi must have two spectral invariants and not three. So, so in the remaining time, I would like to sketch a proof of this theorem about C0 continuity of gamma, and on symplectically spherical case. And in fact, this proof, some parts of the proof were already known many years ago. So there is only one small ingredient which we needed to complete the proof in the high-dimensional case. But let me first, so I will maybe continue from here. So one ingredient, I call it step one, is something which was observed in 2012 by Seyfadini, and it's some partial statement of this theorem that let's consider our M and assume that B is a ball in M, just an open topological ball. And I want to consider a subset of Ham M omega, which I denote by Ham M minus B omega. Those are just phi from Ham such that phi are identity on B. And Seyfadini have shown the following theorem. From 2012, that restriction of gamma to this subgroup is always C0 continuous. So if you require that, look only at those phi which are supported outside some open ball, then gamma is always C0 continuous, and this the idea of the proof goes back to Viterbo, and later Seyfadini generalized it and called epsilon shift trick. So roughly speaking, idea that is that if this is M and this is our ball, we can take let's say C2 small autonomous Hamiltonian, just a C2 small function on M whose all critical points lie in the ball, and let's say this is H, and for any phi which is C0 close to the identity, we compose phi with the time one map of H. And we know that if all critical points of H lie inside the ball, then outside the ball all the points slightly move. So if phi is C0 close to the identity, we know that for this composition, there will be no fixed points outside the ball, and inside the ball, it will be exactly fixed points of this map, and because phi is identity inside the ball. So we know exactly who are fixed points of this map, and we also know what are the actions of these fixed points, because again, by this condition, and this allows us to conclude something about phi. No matter which phi, what phi is, the most important that it's identity on the ball and C0 close to the identity. So this is first step, and the second step is of the proof is what is called C0 fragmentation. So let me first consider the case of dimension 2, and in this case C0 fragmentation is true. And so what is the statement? Let's assume as before that B is some ball in M, and we choose some larger ball which contains B with its closure, slightly larger ball, and consider the open set U1 is B prime and U2 is M set minus the closure of B. So these two sets cover M, U1 union U2 equal to M. So one is just inside ball B prime and the other is outside of smaller ball. And the following proposition was proved in by Antov, Polterovich, and P. It states that if phi is Hamiltonian diffeomorphism, which is sufficiently C0 close to the identity, then one can decompose phi into product of two, phi 1 and phi 2, such that phi 1 is supported inside U1 and phi 2 is supported inside U2, and phi I again is C0 close to the identity. So this can be proved by elementary way methods in dimension 2. And once we have this statement, then the C0 continuity of gamma follows from this theorem and from this fragmentation property, because then we can write that gamma of phi by triangle inequality is less or equal than sum, and each of them is small because we know that phi 1 so phi 1 vanishes outside of B, is identity outside of B prime, so it's identity on some ball if we assume that complement of B prime has non-empty interior, and phi 2 is identity on B, so both of them are small, and therefore gamma of phi is small. But so this is true in dimension 2, and this was how Seyfadini proved his result in dimension 2. But actually, in higher dimensions, such statement is completely unknown in any situation. So this is very interesting if if C0 fragmentation is still true, at least maybe in dimension 4. but it's completely unknown, and we cannot rely on it. But what helps us in high dimensions is one observation which I can call a doubling trip. So the idea is not to look at phi, but so we have our phi diffeomorphism of M, but the idea to define big phi, which is a map of not of M, but of M cross M. This is product of phi times phi inverse. On one component it acts like phi, on another like phi inverse, and we know that gamma of phi inside M cross M by Kunet formula is the sum of gamma of phi and phi inverse, which is twice gamma of phi. So it's enough to prove that gamma of big phi is small. But it turns out that unlike phi, we do know that big phi means C0 fragmentation. So maps of such specific kind, which are C0 close to identity, one can one can prove the same statement for some specific cover of M by two open sets. Okay, so that's what I wanted to tell, so thank you very much.